Hello, this is simply about networking protocols, and today I'll tell you about OSPF topologies, cost of the routes, cost-based route selection, and where ECMP appears and how it is used in this environment. Specification that describes this behavior is RFC 2328. In this video, I'll tell you about representation of the autonomous system of or OSPF area as a graph where the cost appears and how those costs are used, route selection based on the cost, and where ECMP there appears and how it works and what are dependencies for ECMP. So, from the OSPF point of view, autonomous system or OSPF area topology is set of routers and networks and interconnections between them, where interconnection between router and network means that router has an interface in this network, and interconnection between routers mean that there are two interfaces on those routers that are connected to each other, and they are configured in the way that routing is possible using this hop. So this topology can be represented into graph form, or not exactly tree, graph form, with one of the entity as a root, all other entities as vertices, and interconnections are edges. This also can be represented in table form, where everything is very simple. There is a connection between two entities or no connection between two entities. That's it. Then, to specify how costly it is to send traffic from one device to another device, or from one entity to another entity when they connected between each other, costs were introduced. Cost is a value condition of the egress interface. It means that cost specifies how costly it is to send traffic from egress interface to the next hop or to the network if this is connection with the network. In this case, it is cost 10 to send traffic from R1 to R5, 3 to send traffic from R3 to R4, and 4 to send traffic from R7 to network D. We would expect that those values are configured by administrator, or administrator configures conditions if those values can be calculated automatically. So we would expect that administrator is lazy enough or smart enough, or both, so those values will be symmetrical. It means if sending traffic from R1 to R5 is 10, then sending traffic from R5 to R1 is also 10. This is not necessary, but in general, yes. So we can even fill table similar to connections with table similar of costs, with one big exclusion. Cost of sending traffic from network is 0. Requirement by specification. So if you need to calculate cost of sending traffic and you're building topology and graph in the way that root of the graph is some network, then sending traffic to the router, cost of sending traffic to the router is 0. You should remember this when filling in this table. Well, let us back to the topology and graph where root is R1. Since we have values or costs for each interconnection, we can calculate the cost of route between R1 and every entity in this topology, where full cost will be sum of costs on routes, on edges that this traffic should pass. And we can fill eventually a similar table where for a graph where R1 is a route, column with R1 is filled in. For a graph where R5 is a route, column with R5 will be filled in. Well, how you see, in the cell of distance between R1 and R7, we can get there by two possible paths. Those paths or routes are following: R1, R3, R6, R7, or R1, R3, R4, R7. We are calculating cost of route of both routes, adding them to the table, and in the cell we have those values 10 and 11. Well, I would say that common expectation would be that we simply selecting smallest value, and that's it. We have selected the easiest way, or the less costly way, the best path, the best route between R1 and every entity in our topology, and sometimes it is possible. So for R1 we are selecting every route. We know from and remember from the video about general routing that any base traffic will be routed to the neighbor routers. It means R1 anyways will send traffic for further processing to R1 or to R5 or R3. That's it. Only R1 knows the actual target it wants to reach and can select which next hop to use to send traffic correctly by minimum path. This is how it is selected. Here we have 10 and next hop will be R3, and for example to reach network D, R1 can use multiple paths like R5 and then network D, R3, R6, network D, R3, R6, R7, network D, and R3, R4, R7, network D. This value has one minimum value with next route is 5. We are selecting this as R5. Graphically, it can be represented in the following way. All interconnections that will not be used to transmit traffic to entities in this value. In other words, those interconnections that are not part of any best route can be removed, forgotten, and from our system on R1, the tree looks like that. This is the actual perfect graph of reaching every entity in the topology from R1. Let's redraw our topology having R3 as a root. As you see, R3 have more selections, it has more next hops to use, so it could be more interesting at some point. We are taking the column with filled in all possible routes. Again, R3 has multiple destinations to the network D. It can be R1, R5 network D, R6 network D, R6, R7 network D, R4, R7 network D. All those are presented here, and calculation displays that we have two minimum values with different next hops in those. Graphically, we can present it like that. we are removing all interconnections that are not the part of the any best route from R3 to any other entity in our topology, and we receive following graphical representation of appearance of the ECMP group here. So in other words, this value that displays that we can reach from R3, our network D, by two different passes with same minimum cost 12, and we can use different next hops, causes appearance of the ECMP group, and ECMP group appears only for traffic destined to network D. So ECMP is not just a set of next hops available on our system or subset of next hop available on our system. It's subset of next hop available for the system when traffic is set to specific destination. In other words, ECMP group can be used only when sending traffic to network D. So it actually depends on the destination. It's not the destination depends on ECMP group, ECMP group depends on the destination. If or when we have different destination, ECMP group cannot be used. And we should use next hop basing on our table. Other words, when we send in traffic to network D, system on R3 supports ECMP group creation, traffic balancing or hashing, call it whatever you want, then traffic destined to network D on R3 can be balanced between R6 and R4. If traffic destined to R7, for example, this ECMP group cannot be used, and we are using only R7 only pass through R4. And similar to network C, ECMP group is not usable. We should use another path. This is how we calculating possibility of the ECMP group creation basing on the final destination of the traffic that will be processed, and selecting best route to reach the destination on every router. That's how simple it is. Have a great day. Bye.